All right, so we're just gonna figure out why the projector's not working in the classroom. There it is. So hope everyone had a little nice little break last week. Last week I was deathly ill, and then we had the cancellations because of weather. So hope everyone had a little bit of a break. I have adjusted the due dates accordingly. And if I haven't, I'm gonna double check that tonight because I don't want quizzes to be due until a week after I discuss them. That way it gives you time to go back and watch the lecture again if needed. Also gives you time to ask questions and so on. So tonight we're going to discuss chapters 9 and 10. And then we are going to discuss the final project before we head into break next week. So, and there's no Zoom meeting. I am not doing office hours next week. And we will go from there. So the final project will last, the proposal will be due in 2 weeks from tonight. So the next time that we have a Zoom meeting. So it gives you some time to work on that and think about it over the break. So we will discuss more of that at the end. I am still getting caught up from grading from being sick. So if there's outstanding grades and it's been a while, just shoot me an email, let me know, and I will look at it. Also, if you've emailed me about using flex days for your late assignments and I didn't properly account for them because Canvas can be weird about that, let me know and I will adjust accordingly. So, any questions on that?
Professor, the quiz for chapter 9 and 10 is due this Thursday. Is that going to be moved to next week or?
Yes.
Okay, thank you.
Yes. Don't want to do it now because it might show everybody grades. But yeah, I'll make sure that's due. Again, I don't want stuff to be due over the break, so it'll probably you're going to get an extra week to do it. So,
Okay,
fantastic.
thank you, Professor.
Yep. So also after chapters 9 and 10, the book kind of gets into use cases with IoT. So I may skip around a little bit and might deviate somewhat from that and go more into Raspberry Pi and just Linux-based stuff based on your guys' feedback with the past couple of discussion questions that I posted. Yes, I did hijack those questions so that I could get feedback and figure out what people need to work on. So I will be planning my lectures according to that stuff. Most people want to learn about bash scripting. Some people just need refreshers on Linux from the beginning. And I have no problems going over that, especially when it comes to the Raspberry Pi, because it is such a fun platform. And there's a lot to learn about it. There's stuff that I've never even used on the Pi. So we will go into that. So I will share my screen. I don't think I've done that yet. We get into chapter 9. So chapter 9 is more about interoperability. And we've talked about interoperability probably 9/10 of the lectures because it is so very important to IoT. So there's kind of two different types of IoT interoperability. There's your technical interoperability, which is your hardware, your software, your platforms. Does that work together? Does it have to work together? Because sometimes you have completely separate devices that they are on the same network, they're providing data, but the devices don't actually need to communicate. Like, take a hospital, for instance, you have a heart monitor that's working for a patient, but you also have like glucose monitors. The heart monitor and the glucose monitor don't ever need to talk to each other, but they're on the same network and they're all sharing data, which is where the syntactical interoperability comes into play. So that is your data formats, including the syntax and encoding. Your devices, if you want the data to work together, they have to be syntactically interoperable. So on the back end, it may combine the data of the heart monitor plus the glucose monitor and send it all to the nurse's station at one central monitoring location. But those devices don't ever have to talk to each other. They can be completely different protocols. They can have different cadences for the data. So there's different degrees of interoperability. So also with this, within domains, like data domains, the standards that you're following for your interoperability provide long-term efficiencies of solutions. What does that mean? That means that like all of your heart monitors are going to work together really well. All of your glucose monitors, they're going to work really well together. If a glucose monitor goes down, it doesn't matter. You can just swap it out with another one and it will work. That's because the hardware is technically interoperable. So you have kind of siloed devices just working together on a shared standard. So it's a long-term solution. But between the domains, like the heart monitor, glucose monitor, I'm going to keep going back to that because it's a really good example of this. The standards encourage collaboration. So you have the nurse's station that's combining all of this data from all the different devices related to the patient and putting it in one place for the nurses, the doctors, the PAs, everybody to just monitor. And sometimes that even gets recorded into the patient's medical record. So your software has to be able to handle all of that data. And we're going to get into the messaging and how data is actually sent today. So any questions on the two different kinds of interoperability? So this book kind of skips around some. So we have some inherent characteristics of IoT devices. So there's multifaceted devices, different types of systems that may need to communicate. We've kind of already gone over that with my example of items in a hospital. High diversity. Your glucose monitors are not going to be the same make and model for the entire lifespan of your hospital. So you have to be able to be resilient to version changes. And sometimes you have to go back and forth based on your needs. Sometimes you have to pull items out of storage. During the COVID pandemic, when it first started, so many hospitals had to pull ventilators that were outdated out of their storage facilities because they needed to utilize those for the patients. And there were some issues with data not being transmitted properly or not at all because some of the devices predated data transmission. So your systems kind of have to be resilient to that to an extent. In an emergency situation, you don't care so much about your data as much as your patient. Patient always comes first. Now, I work in healthcare full time, that everything goes back to healthcare. So your systems have to be interoperable with each other. You have to be able to handle those different kinds of devices and manufacturers, but you also have some level of acceptable non-interoperability. So being dynamic and non-linear kind of also falls into this because new devices have different data structures, different protocols. We'll get into data structures a little later on tonight, as well as protocols too. But just the way data is sent from a device to wherever, is it being sent along the same messaging bus as your other data? And again, we're going to get into messaging bus quite a bit more later. But this path is not always the same. So your devices may be able to communicate, they may not. It's just how are you handling your data? That's what it comes down to with IoT is you're getting your data from the environment, from a person, from an observation, and that data is being sent somewhere and being used in some way, whether it's just observation or you're using it to make changes like a furnace and an IoT thermostat. Your thermostat is reading the temperature, making the decision to turn the furnace on or off, and then affecting that change. So the next part is complex data quality. There's a lot of data formats out there. There's a lot of data models, and because of that, there's so many different diverse models. Like your Fitbit is gathering your heart rate data, it's gathering your some of them can do blood oxygen levels, so I wouldn't really rely on that. It's monitoring your sleep. So is it sending each of those as a separate message, or is it combining all of them into a single data model and it's sending it more in a packet or a single JSON message, for instance, where it's a key pair where it says heart rate 82, respirations 12, SpO2 98%. So that's kind of your data structure and your models. And then how are you storing that data? How are you securing that data so that I can't look at someone else's? So that the security is more on the back end, a little bit on the front end, because I don't want somebody else pairing to my Fitbit and getting my data. So security comes into play there. So any questions on any of these points? So standards in IoT are, how should I say this? There's a lot of them. This is a quiz question, 2014, which 10 years ago. There were over 400 related standards to IoT. 400 of them. Some of them are more broad spectrum, like 802.15.4, which is an IoT communication standard over radio waves, similar to Wi-Fi. Some standards are manufacturer specific. So like the manufacturer or the microcontroller manufacturers, they publish their own device level protocols, and cloud vendors do their own protocols, and so on and so forth. So there's a lot of very specific protocols out there for a very specific purpose. And you're not going to take a communication protocol for a Fitbit and use that for cellular communication, because it's not applicable. It won't work. Chances are, if you're in a modern day and age and you're trying to communicate wirelessly with a device, there's a standard already created for you. It's probably IEEE, or it might be an ITU standard, but there's probably a standard out there for something that you want to do today. A lot of these standards are simplified by modern technology. You probably won't see 3G networks being used anymore. They have pretty much gone away. They were turned off. I want to say AT&T shut theirs down in 2016, 2017. But now you have 4G and 5G, where 5G it's still up and coming. There's still some areas in the country that do not have 5G, but 4G is pretty much everywhere in the entire country.
Can I ask something real quick?
Yeah.
I thought it was only until recently, like I remember in the last 2 years is when they said they're going to shut down the networks. I didn't know AT&T was doing it earlier than that.
I will double check, but I know in a previous job, we had issues because we had a device that we built that did at-home physical therapy for knee,
Yeah,
replacement
'cause
patients.
I know Australia literally shut down their whole 3G infrastructure, like in the past few since 2021. I know, but I've heard about that from a YouTuber I watch who lives over there, and how many issues that caused.
Double check. They may have also pushed the dates back from when I noticed. But we had these devices that did physical therapy at home, and it sent all the patient data in through a 3G cellular modem. And we were told in 2016, 2017, AT&T is shutting down their 3G network. So we spent a ton of money to upgrade those to 4 and 5G modems. Could they have changed their mind? Absolutely. And I'm kind of seeing that may have been the case. So
Yeah, because I just know because it's still causing so many issues, even with how bad the Australian shutdown went, that they
yeah,
keep pushing it and pushing it back.
after I left that job, I sort of stopped caring because it wasn't my problem anymore. So I may have just given bad data.
It's
Um,
okay. Things change every day.
But exactly. So a standard that you're relying on today may not be here tomorrow, or it may not be full capacity like the 3G shutdown. I do know that they were shutting it down in waves, shutting down kind of the smaller markets first. So that's something to keep an eye on. That doesn't mean you have to be on the bleeding edge of technology. 4G has been around for over a decade now. 5G is, like I said, still up and coming. That's probably still got a decade in its life left. I do know 6G is underway in research. Yep, 6G is being researched right now.
How could you even do that? I thought we were at the pinnacle right now.
We're at the pinnacle for today. But in the Industrial Revolution, we thought that coal was going to be the primary way to power things. So
yeah, I did research. I think it was for IT 110 that I talked a little bit about it on our research paper. But it's been in development since even before 5G came out. It's like saying with 5G, they just start way ahead of time, mostly in the academic sense, because it's just you got to start with the theoretical.
Yep. Actually, as an undergrad, I did a little bit of work on spoofing a 5G tower using some some specialty radio equipment. And basically my conclusion was that it takes a lot of money to do that.
Yeah, and who knows how, because like with the 5G rollout, it was pretty slow to begin with. Just imagine what the 6G rollout would be. It would take a lot longer than 5G has.
Yeah, and some of that is cost. Like the antennas and the equipment is just not cheap. 5G has a much shorter effective range than 4G, so you need physically more towers to cover an entire area. And that's just the way that those wavelengths work.
Yeah, because like I've heard stories with 5G of people literally just walking around a building or behind a tree.
Yeah.
And losing signal.
Yeah. So there's a lot that goes into a nation and worldwide rollout of these technologies. So we'll probably be hearing about a 6G rollout 2030, 2032, roughly. So moving along, we have the different, most people have heard about the OSI 7-layer model in networking. Most people, myself included, can't name all the 7 layers anymore because you remember for a test and then you immediately forget about it. So I don't blame anyone for not remembering it, but there are a few layers that are very relevant when it comes to IoT. The first one is your link layer. So most people don't think of the physical layer as being like, well, most people think of it like the copper wire or the fiber optic, but a lot of people forget the radio wave because the radio wave is your physical layer at that point. My master's thesis was about interrupting the physical layer for consumer drones as it relates to privacy and trying to deter drones in private settings. Half of that paper was, this is how you do it, but don't do it because it's illegal. But most security people don't think about interrupting the physical layer, whether it's in networking or radio, but that's oftentimes the most overlooked when it comes to device manufacturing and design. So physically, how your device communicates, how the packets are coded and signaled is very actually kind of a weak point, because data can't get through if it can't communicate. It doesn't matter how secure your data is. If the desire is just to disrupt communications, like a denial of service attack or complete disruption, generally the physical layer may be the best. So that's something to think about. On top of the physical layer, or the link layer as the book calls it, I still call it physical. I don't know if that's changed. You have your network protocols, which is responsible for sending your packets and your routing. The most common is IP. Mostly we use IPv4, which is 32-bit addresses, and IPv6, which is 128-bit addresses, which has been rolling out for 20 years at this point. Not a lot of services force IPv6. And actually, if you look at most computers, they have both an IPv6 and an IPv4 address. So that's kind of a phased rollout that's probably going to last another 25 years until all the IP addresses are taken up by something. But IPv6 was created because there just weren't enough IP addresses when it was first conceptualized. Or there was enough when it was first conceptualized, but then the internet took off. It was more than just a fad. And now I have 40 IP addresses in this one classroom that I'm in. So the IP address space is a little crowded, and it doesn't help that there's a lot of invalid IP addresses. Like all the 127 dot whatever addresses, those are loopback addresses. You can't use those for talking to another computer. There's also the 169, there's 172, there's internal IP addresses only, 192s. So there's a ton of address space that just can't be used by the internet. And that takes up even more space. So you're limited in that regard as well. Now, IPv6 still has space issues, but it's not nearly as bad, and it is going to offer a ton of growth, and probably, I'd say probably 100 years will fill it up, and then somebody else will have to come up with a new solution. But IPv6 was the direct replacement for IPv4. I don't know what happened to 5. We just kind of skipped it. But one of the protocols the book mentions that I've seen used in IoT devices is 6LoWPAN, which is a low-powered IPv6 version that works with 802.15.4. It's meant for not a ton of communication. It's very spurious. It's not meant for like streaming data. It's you're sending a few packets and then the signal might go dead for an hour before it needs to send again. So this is a protocol that's used with some IoT devices. But generally, most things are going to be IP V4 or V6. Bluetooth has their own addressing as well. That basically uses the MAC address as your ID number. So every networking device on the planet has a unique MAC address that corresponds to just that device. And so Bluetooth just uses that usually as their identifier. So makes it easy. So next up in the layer is the transport protocol, which controls error control, your packet segmentation, and your flow control, which basically means, is your data getting to where it needs to be in the order that it needs to be? And there's basically two different protocols that are used, TCP and UDP. And this little graphic kind of it demonstrates the difference. TCP is an exchange between the two computers. One computer is sending the data, the other computer sends an acknowledgement. And if that acknowledgement's not received, computer A is like, oh, I need to resend this again. Or if computer B says, well, I got this out of order, can you send the previous frame again? So the computer A is like, absolutely, let me just get that right out to you. UDP is different. It's I'm sending my data. I don't care what gets it or how it gets there. It might get there out of order. It might not get there at all. I don't care. I'm just faster.
That's what you're saying UDP is.
Yeah. Yeah. Because UDP, it will hopefully get there, but because it doesn't have that exchange back and forth to verify each packet, it's much faster.
Doesn't it just blow it up in an area and tries to get to its location? Like it doesn't know where exactly it's going.
No, kind of. This UDP should still be going to a specific IP address and port, but you can have a multicast UDP that's going to multiple devices.
Okay.
If you are broadcasting UDP just openly, you probably need to re-architecture that project. But there is no verification, there's no double checking to get it, to make sure that it's out of order, or to make sure it's not out of order, sorry. There's not even checking to see if the data was received. Now, if you are building a project and you're using UDP and it's great, and then you're like, well, I just want to make sure that the data is getting there. So now you're manufacturing an acknowledgement at the end where you're saying, oh, I've received a UDP packet. I'm going to let my server know. Well, now you've artificially created TCP and you've just slowed down the entire process. You may as well just use the TCP that's built into the networking card, because the network card can do it a lot faster than your software. I guarantee it, unless you're an FPGA programmer, and then that's a different story. I have a friend that works for a company that does the webcams on highways in Michigan. Some of those webcams are TCP, some of them are UDP. The TCP ones tend to have more issues than the UDP, because TCP expects pretty much a constant connection. And if anything breaks that connection, if your device isn't able to handle that gracefully, in the case of these webcams that the state spent tons of money on,
Awesome.
they just fail. They have to be restarted. But the UDP ones, they're just sending out the images. They don't care if they're received. They have the fewer problems. So these webcams, they aren't recording anything. They're just used for live monitoring on the MI Drive website. Let me pull that website up. So let me make. Want to look at cameras? Here's a camera. Stream not available. Of course. Actually share the right screen. Okay. Can the people on Zoom see this screen?
Yes.
Okay. So these webcams, most of these are UDP based. The state doesn't care if the data actually gets to this website because it's not being recorded. It is just live monitoring. Anybody can go on, click on their route, be like, oh, traffic looks clear, or traffic's not that great. So I'm going to go to Google and see what I can do to either route around it, or maybe it's going to clear it by the time I'm going through. But all of these cameras through the entire state, I'd say about half of them are UDP, half are TCP. So the state's servers that are driving this website have to be able to take all of this data from all these different webcams that are sending with different protocols, and they have to be able to present it to the user on this page. So this is a technical interoperability, or it's more syntactically interoperable because you have the different devices, different protocols, but the same kind of output.
Why does it allow you to even do what you're doing right now?
Because your tax dollars paid for
Oh,
it. That's really
'cause
what
that-
it is.
this seems like a police kind of thing you'd have.
But these cameras don't record who's going on them. It can't even read license plates.
Oh.
It doesn't record anything. It doesn't even show the speeds of the cars.
So what is it showing?
Traffic conditions in various areas.
Oh,
That's really all it is. Just traffic conditions. Sometimes they don't work. Sometimes they take a while to load because I'm kind of viewing them asynchronously. Where it may not have an image in cache and I may be waiting for the next time the camera sends a picture. Like this one came up right away. This one needs to be cleaned. So the state also uses this to monitor traffic flow patterns, especially through construction zones. They can use it to monitor construction projects. But this website is kind of the culmination of all of these devices and all the data being sent to them. So it's kind of a fun thing that your state offers. And all the way up into the UP. So that's kind of a brief TCP UDP. I do know some computer games use UDP if it doesn't matter what order the data comes in. If you're trying to play a multiplayer game and you're trying to keep track of multiple people, you definitely want your data in order because you don't want players to be jumping back and forth, which is what would happen when data is out of order. You get kind of a slingshotting effect in the game. Then you come to your application layer protocols, HTTP, like that website. There's also the advanced message queuing protocol, which is, we'll talk about that a little later on. And then you have the extensible messaging and presence protocol, which is an XML based protocol. So anything that can consume and display XML, even like homebrew software, could use XMPP and utilize the data that's being sent out. All right. So this is straight from the book, copied and pasted. These are various use cases, the application, basically the 4 layers that we talked about, and the protocols used. You're going to have to think about this for the project, for the final project when you design your own IoT device, because I'm going to ask you, what protocol are you using in your application layer? What does your networking layer look like? I can almost guarantee you everybody, most everybody, is going to end up using this one. The web-based IoT application with negligible power constraints and landscape. So your Raspberry Pi is probably going to be the heart of your IoT. I am giving you the option to either use your Raspberry Pi to ingest data or to be the sending portion of data. So, because every IoT network has your device that's reading your data and then whatever is displaying your data. So there's,
Can you give an example?
yeah, like your, let's use the Fitbit example. Shit, I'm not even wearing one right now. Fitbit's collecting the data. Your phone's displaying the data. Your phone received the data, it's displaying it. We're gonna skip around the whole, it went up to the cloud, got reprocessed and then sent back down to your phone.
Yeah.
But your phone still is that gateway to the cloud. So it collected the data. So still kind of working on the parameters for that kind of the part of the project, but basically if it can accept dummy data from a device, because let's face it, a lot of students in this class aren't going to have the sensors available for what they really want to do. But if you can describe a data structure and be able to ingest that kind of data and then store it, process it, display it through web page, script, whatever, that is perfectly acceptable. So your application layer, HTTP, web. I prefer HTTPS, but it's just one or the other. Transport layer is going to be TCP, pretty standard using IP as your network layer. So you see in your networking settings, you have TCP/IP. That literally means TCP over IP because it's using the IP to transport the TCP packets. And then your link layer, there's a myriad of options, 2G, 3G. See, this book doesn't even have 5G listed under link layer. Why? Because the book was printed in 2018. So 802.11, which could be ABGN. There's 10 different 802.11 standards now. It's Wi-Fi. I won't expect you to be able to identify the standards because most of them are interoperable with each other. They're backwards compatible. So if you're using Wi-Fi, just say Wi-Fi. I don't expect you to say, well, I'm using only 802.11n. That's just, nobody uses that. The other,
You said 802.11n? What are you talking?
this 802.11 here,
Yeah.
just, it's all Wi-Fi.
Okay.
Usually there's a letter after it, like ABG.
Yeah.
But 802.11 is your Wi-Fi standards, and then you have the substandards from the IEEE.
Okay.
So I'm not actually even sure what the current Wi-Fi 6 standard is, but it's 802.11.
We're all gonna be using that because the Raspberry requires the hotspot via your whatever you're using. Is that
9 times out of 10, most homebrew IoT is going to be using that anyway.
what do you mean?
Regardless of if you're using a Pi, using an Arduino, FPGA, you're going to be using Wi-Fi or cellular as your communication. You're not going to go into 802.15.4. You're just going to say, well, we're going to communicate over Wi-Fi.
Okay.
And that's 9 times out of 10 how it's going to be. Or cellular. Cellular is the other option.
For you talking about like cellular hotspot? Is that what you're
Yeah.
saying? Oh,
Yeah,
okay.
like if your device is meant to be stuck in a field somewhere, you're not gonna have Wi-Fi out there, you're gonna have cellular. But we'll kind of get into that a little later on with your project, and we'll discuss some of the, oh, got a channel. So your projects are mostly gonna just be Wi-Fi. If it's meant to use cellular because it's a device you've designed that goes remotely, fantastic. Just say that you're using cellular. I don't expect you to go out buy a cellular hotspot. a plan, SIM card,
I hope
etc.
not.
University won't let me require that. But this is basically what your projects are going to be based off of, is these 4 protocols. Now there are some interesting ones on this, like IoT application with large data volumes and open interoperability requirements. And this is using an advanced message processing queue. The AMPQ application layer is interesting because it can be used by a ton of different devices. If you can script with Python, you can ingest this data. Amazon Web Services has a service that enables AMPQ for your services.
Why do you use the word ingest? What do you, like, I understand that you're meaning that it
So-
should take in the information, is that if that's what you're.
Yeah, so what is data ingestion? When your device sends out data, it's going to be in a raw format, whether it's JSON, XML, CSV, something. That's not usable by anybody. That has to be ingested into a database by some
They can translate.
system
Okay,
that makes it readable to a human.
okay.
So as a raw format, it's pretty useless, but so once you ingest that data and normalize it, now it's useful to everybody. So ingesting is just a data engineering term. You have your data come in, you ingest the data, you use the data. Kind of like food, you ingest your food, your body uses food. And that's just how that works. Wow, it did not clear. Clear all drawings. Okay. So chapter 10 is all about publishing and subscription systems. So this is where your data ingestion kind of comes into play, is your data is being sent out. Now it's got to be used. And how is it going to be used? How is it going to be stored? How much data loss, if any, is allowable? If my Fitbit misses an hour of data, who cares? If a critical infrastructure misses an hour of data, it could be life and death. So, so this is what we call a message bus. Has anybody ever heard of the CAN bus in a car? So modern cars, 2013 and newer, some 2013s before had what was known as the CAN bus, but 2013 was when the government mandated it. Basically, all of your devices in your car are talking on a network. If you see on your dashboard, oh, your headlight is out, that is your headlight communicating with that CAN bus or lack of communication with the CAN bus, and your computer's body control module saying, oh, I haven't gotten a message from the headlight saying that it's turned on. Well, now I'm going to show a light on your dashboard because, well, the light, I think the light's burned out. So your car has a messaging bus in it. Modern cars have a messaging bus in it. And that data is used by mechanics, it's used by performance tuners, and new devices and applications can be added to this bus as long as there's space. Now, your car does have space limitations on how much data can go on that bus just because of the structure of that network. But that's the general idea, is that you've got all these devices sending out data on a common line. And that common line can be read by any other devices on that line. So in our application, we're not really looking at raw data. Your car's headlight is using proprietary information. Like it's sending out messages in a proprietary format that only the car knows. But in an IoT infrastructure, you may want to add or remove services at will that are using your data. So that's why we use the platform independent data formats like XML, JSON, binary JSON. So anything that can read XML on your bus can use that XML. Again, this is data that is still in the bus. You also may have one of these applications be perpetual storage. So like application 6, once the data gets here, it gets dropped into a database. Application 3 might be a live web view of the data that's coming through. Application 2 could be the device that's putting the data on the bus. Now, data does go both directions. So once you get on this bus, application 1 can also read application 2's data. So think of this like a road. Once it gets here, it just gets split. So 6 could be your data storage, 3 can be your website, and 2 could be what was sending it. There's going to be chances are not all of your applications are going to care about the other applications. These applications are going to be independent of each other in general. Like the data storage should never care that the website is down. If your website,
Isn't that because it's a physical storage unit at that point?
sometimes, yeah.
So why would
Sometimes
it
it's the
care
same
then?
server, sometimes not.
Why would it not care then?
Because if your website is only viewing the active data on the bus, like the most recent data, it shouldn't care that there's nothing there to actually store the previous data. Like your website shouldn't crash if it's just meant to view live data. Now, if it's trying to view historical data, your database server's down, it's not going to work. But like your database server is also not going to care that there's a website up for the other data. So they're very siloed apart. Some developers will put them on the same server, especially if it's not critical. But if you're in a large infrastructure, they're going to be separate. So that way, if one system goes down, it doesn't bring down everything. So any questions on that one? Any other questions, I should say? So I kind of already alluded to this, but data on the bus could be synchronous, where like the website might be showing just the live data that's being transmitted right this moment. Or it could be asynchronous, where the website is now viewing the data from the database, where it doesn't care what data is currently coming in. It's just looking at what was already sent at a later date. So that's kind of like how these classes are set up, where I could upload a lecture and it just sits there in storage and you view it at a later date, or you could be watching it live via Zoom synchronously and be able to ask questions and work with the data. All right. So discovery. So this kind of is a little self-explanatory, where as soon as a new device starts sending data on the bus, that data should be available to everything. It should just incorporate with your message bus, and the new data should be accessible by your data storage. It should be accessible by the website. It should be accessible to the end users, whoever that may be. And also, your data should not be expected from disconnected devices. This seems self-explanatory, but let's say your data storage is harvesting all the data on the bus, it's storing it properly, and then all of a sudden device number 4 is taken offline. Well, your data storage shouldn't be waiting there for device 4 to resend. It should just be processing what's on the bus. Data 4's data is just gone because it's disconnected, it lost power, whatever the case may be. But in no instance should your devices be expected to be sending data. Is there any questions on that one? I don't feel like I've explained that one well. Basically, if the device is offline, it shouldn't be expected to send data, and it shouldn't prevent other data from being stored or used.
Isn't this when though you would, if you have one that's having a problem, then you could have like a fallback? Is that what we're talking? It sounds like it,
It's possible you could have a fallback option.
but it wouldn't
Where-
be using a car.
No. This is more, you've got 10 sensors and all of a sudden now you're only getting 9 sets of data. Your storage application should never be waiting on that one set that's just missing in order to proceed. So it should just store everything. It should display everything nicely, but it shouldn't be like trying to process data that's not there from a device that's offline. If you want to show a message to the user, hey, this device's last data was sent 2 days ago, and alert the user, hey, this device is probably offline, that's a good way to handle device failure. But otherwise, your message bus should just be a constant stream of data from your other devices that are working and are online. And with that being said, each device should not be reliant on another device. So just because one is offline doesn't mean the other one should not be sending data. Storage. What happens to the data on the bus? Like I kind of said before, you've got one application that's just meant for storing data. How is it storing the data? There's time series databases, NoSQL, SQL-based, multi-model that might combine the two. Snowflake is a cloud database storage that can do JSON within a relational database. MySQL is also able to do that. So there's a lot of different options for how you store the data. Most of this is going to be non-volatile storage on hard drives or solid state drives. If it's in the cloud, it doesn't matter. You're probably not going to be picking what kind of storage medium your stuff is on. There are also memory-based storage options where everything is stored in memory for super fast data writes and reads, but that will increase your cost.
You have a ton of space there.
Exactly. But if you have some kind of mission critical data, let's say you want to store the last half an hour in memory, and then after that half an hour, move that to a solid state drive. That's a hybrid option that's also possible, where just the most recent stuff is stored in memory. So there's costs, there's cost versus time. Like, how critical is it that you shave those few milliseconds off? There's only a few instances I can think of where that would even be applicable, but I do know they're out there. Most of them are in healthcare. Some of them are in, say, like deep sea drilling. You probably want some up-to-date information where seconds matter because you're drilling so deep in the earth, it takes a while to get data up and down. So anytime you can shave off, the better. Space exploration is another one where you want the most recent data at your fingertips and you don't want to wait for any lag time. So your storage, there's a lot of different options. You can store the raw data as well as your database. Some cases where that might be applicable is if you still want the raw data available for analysis. You don't want the stuff that's been parsed out and transformed into something human readable. You want the machine readable data, or like machine learning is a good case for that one. So this kind of is, I stole this from someone. And credits are at the top left. But this is kind of a breakdown of some of the different kinds of databases. And I talked about the relational, the SQL, and the NoSQL. Time series databases are exactly how they sound. Everything in the database has a timestamp, and as such, it makes it very scalable as well as fast for searches. So your relational databases, that's going to be 98% of your websites out there use relational databases. If you go to Amazon, they're using relational databases to store all their product information. NoSQL is interesting because it's basically JSON's object storage as a database, where it's key value based, and they call it document based as well. So most of the stuff is going to be relational, but NoSQL has been taking off over the past 15 years or so. I can't wrap my head around NoSQL. I have tried, but I can do SQL all day, every day. That looks like a duplicate of the slide I already did. No. So along with your message bus, you have to be able to process the data, which is to make sense of it. So you're getting this data in that humans can't really read. It's not pretty for your end users. So the data has to be processed. In the past, high performance computing was used to process these large batches of data, but as computers have advanced over the years, you don't need what's still referred to as high performance computing. Your Raspberry Pi is perfectly capable of processing most data. You don't need a supercomputer to manage most sensors. If you're managing a network of weather satellites, yeah, you might need something a little more power, but in general, it's not needed. And then there's also Apache Hadoop, which can deal with streaming data and also distribute that amongst all the computers that you're using. So for instance, like this classroom has probably 30 computers in it. If I had data streams coming in, I could install Apache Hadoop and process all of the data synchronously between all of the computers and split up that workload. So what might bog down one computer is now spread amongst 30, and they're all kind of a cluster working as one.
That'd be like, that'd probably have to be really slow though, right?
Not really. So while the data is getting processed out, there's generally one or two controllers that's kind of controlling the entire process, and it's sending out the work in batches. Just as work comes in, it's dispatching it to all the computers, and then the work is sent through the pipeline. You have your giant 30 computer cluster acting as one CPU, and it's actually quite a bit faster.
So it's not in the same form as like Zoom, where we have you put up the video and then we can all see the video on our computers. It's
No, each computer is getting a chunk of the data, processing it and passing it along. So it's literally splitting up a giant piece of data into 30 different slices, saying, process this, and those little slices just get moved through a lot quicker because they're much smaller.
Where would you even use that?
Big data processing.
Because that sounds really niche.
It is, and you're not going to use it in this class.
Okay.
That is used a lot with world simulations. It's basically the architecture for supercomputing.
Okay.
So unless you're planning on running a supercomputer, I have
Okay.
installed Hadoop on Raspberry Pis. I had a cluster of 4 Pis.
They fizzle out.
And it worked. It wasn't pretty, but it worked. I used it as a password cracker for one of my classes as an undergrad.
That's cool.
So it definitely can be done. So this is kind of the architecture flow for cloud-based IoT. And what we're going to focus on in this one, the device tier, it's self-explanatory. That's all your sensors, your gateways, how everything communicates. Like your sensors, give you your Fitbit, which makes your gateway your phone. And then the cloud tier takes in those messages. So the cloud tier, this, I guess, represents the message bus. And then you have your so-called value-added services. But the main ones are storage and visualization. Like, who cares about the raw data of a Fitbit if you can't see it in a pretty graph? And that's what this does for you. It stores your data and it visualizes it, and then that is sent back to the messaging system. And then that can go to your user-facing application. Sometimes it goes direct to the user, sometimes it goes messaging system. There's a couple options here. Yes? Question from Zoom?
Something. But someone said something.
I'm not sure. So your storage, your visualizations, once that's done, it gets to your user-facing applications, sometimes through your message system, sometimes direct. I'm not actually sure which one Fitbit uses. I keep using them as an example, but for some reason, they won't send me their reference architecture. I don't know. So
This is the big key, and it's all been mine. It's part of my big one. Like this video is sponsored by Big Key.
all right. Okay, so message-oriented middleware. Go back. So I've discussed the message bus pretty much at length tonight. So what is the message-oriented middleware? This decouples the message producers, which is the devices sending out the data, and then the consumers, what's ingesting and using the data. So there's 3 different ways that this could be disconnected. You have your time, where your producers and consumers don't necessarily have to be connected at the same time. So what does that mean? Back to the Fitbit example, when my Fitbit is dead because I forget to charge it all the time, or it's just not connected to my phone, but it's still collecting data, it will still collect that data until I connect my phone again. Sometimes I don't have the Bluetooth on my phone, and it just stores the data, and then it sends the messages once it reconnects to my phone. That kind of goes both ways. The phone could be dead as well, or whatever's using that data. So the data is in storage on the device until it's able to be sent. So that's kind of an example of time decoupling. Space. So in a message bus, messages are not really addressed like to an IP address. So I'll discuss this on the next slide, but in a simple message bus system, you have what's called topics or channels. I think AWS simple notification service calls them topics. Basically, you have a subscriber, like I want, let's say I've got a network of weather stations. I want the wind data from all of this. So I look on the channel or the topic for wind, which my devices are sending out, and I get all that wind data. Or I may have one that's precipitation data, and it could be segregated out that way. And anything that's subscribed to that channel or topic can use the data from that channel or topic. But the data is not addressed to like 192.168.0.1. It's just addressed to that message bus and the topic. And your devices can be addressed to multiple topics. Like you can have a wind and precipitation, you can have an overall aggregate of data. So that's kind of how that works, where I'm sending out the data. I don't care who reads it, as long as you're subscribed to that channel or topic. And then threading. Messages are asynchronous and non-blocking. If I have something on the bus that's taking a while to process, it should not prevent anything else from being sent on the bus. Your bus should be able to support multiple data streams. And the only thing that might be affected is that device that's sending it. For whatever reason, something's blocking that device from sending again. That's on that device. It won't, or it shouldn't affect any other device that's trying to use the message bus. So if you have a failure in your message bus, that's a whole different problem, because now nothing can communicate. So you might need to architect a fallback option for that one. But in general, message blocking should not happen. Any questions on that? All right, so this is Amazon's SNS, the simple notification services. So they have the SNS topic, you have your message publisher. Now these topics are going to various services that are using the data. So you have your SQSQ, that is really hard to say. AWS Lambda functions. I took this from the AWS architecture drawing, so it's all AWS related. But you have your publisher, you have your topic, and then you have your endpoints. Now, at no point does like your HTTP endpoint ever directly talk to the publisher. It always goes through the message bus, the queue, or the in this case, the SNS topic. So this is useful because let's say you have data coming out, and all of a sudden something's weird with the data. You still want to send the raw data to your message bus. You still want it to be able to be used by everything. But now we're also going to send a message along the topic called alert. Yeah.
Are each one of the dotted lines technically a message bus?
Each of those is a message being sent out.
Where's the message bus in the whole thing?
The bus would be right here.
Okay.
So this is kind of the router for it. All the messages come through here. Each topic has subscribers that read that data. So you're sending your data out. All of a sudden, something's a little weird. So now I'm going to send out a message along to the alerts topic. Now, everything that's reading the alerts is going to get that message. Now, that could be like a push alert to your phone, or it could be an email. But now you've got a secondary stream of data along the same message bus that's being used in a different way from your device. So you can have infinite number of topics. Your subscribers can generally subscribe to an infinite number of topics. So you have a really broad spectrum data bus to process and send your data from your IoT device to everything else in your network asynchronously. So if something goes down, let's say an alert goes out, but no devices are online to receive that alert. That alert should stay in your bus, or at least in hard storage until a device comes on and it can see, oh, device, send. So now all your phones that are coming online are now getting push alerts because some data looks weird. So any questions on publishers and subscribers? All right. So this is a sample of JSON. It is used pretty much all over. It's a very modern message type. It has a key, which in this case, message type. And then it has a value, in this case, advertisement. So message type could be advertisement, could be alert, could be anything you want it to be. This is very freeform. You can have as many fields in a JSON document as you want. It can be nested as many times as you want. For instance, data stream here also has the subset of data semantic, which defines what kind of units you're using in your data. In this case, Celsius. JSON is also kind of how NoSQL stores their data. So you can store this in a JSON database. You can parse it out into a SQL database. The options are pretty much endless. So, like this first point says, you can use this message itself to register a new device. Like, all of a sudden, your message bus starts getting this new device ID. Well, I don't have a record of that device ever having sent data, so I'm just going to go ahead and register that device. And now we're going to start adding data to our forward facing, like our website, from this device. So if you're using these messages to register devices on your network, what's one of the big caveats of this? Anyone that can send a message like this can now register a device on your network, nefarious or not. So you have to have some kind of check and balance in there to make sure that somebody's not potentially hijacking your message bus, putting out false data. So you may have this ID number, but you may also have a separate database that cross-checks this ID number, or some kind of checksum hash somewhere in this message to verify the authentic nature of the message. Then that'll just prevent wrong data from being parsed because some hacker got on your device and is now sending JSON and flooding your network with bad data. So now you're starting to get this data from this device. What if you don't receive data in 2 days? Well, that device is just offline. And then it goes into the database as, oh, it hasn't sent data since February 15th. Time to just turn it off. Wait for the next message to come in. Maybe alert users, hey, this device hasn't been on in a while. And you can use all of that just from the data that's being sent without any extra registering or deregistering of devices. In high security, you're going to have a database of all the devices allowed on your network. But in something low security, like for this class, it might not matter. So, any questions on?
Repeat what is the blue square for again? Why?
So JSON is a key value pair. So the blue is what's known as the key. So message type, name, ID, whatever comes first is the key. And then whatever comes next is the value. So the key is type, the value is sensor.
So you're just making one more. Sorry, I think I missed this part. This is for like someone giving you an email, or is this you making variables
So-
for?
This is like your device. This is the data that could be sent out from a device.
To you, from someone to you.
Yeah.
Okay.
So this goes on your message bus. It has your data in it. This one just happens to be an advertisement, which is generally, hey, I'm here kind of message. That's generally what a device advertisement is.
Yeah.
And then it gives kind of the metadata about the device. So like in this case, the room that it's in would be FT425. So this key should never change. This should be the same across all of your devices. This is how you're going to process your data. You're going to pull from your key values. And then it's going to parse it based on the value of those keys. So like my name, the name is the key value, Aaron. And that's how JSON works. It's nested. It's wonderful. It's probably what most people are going to use. XML is another key value based data format. So this is what most devices nowadays use in some format, encrypted, compressed. It always comes down to JSON. And sometimes this whole message is just saved as one field in your database, or you may just pull out the pertinent information that you want. Like, oh, this device is online. The last time it was sent, I actually don't see a time on this message. Most of your messages are going to have to include a timestamp because I have no idea when this message was sent. So that's kind of a short-sighted on the books case, but all your messages are going to include what device it came from, what time that data was sent, and the data values itself. Sometimes there's more than one. Like,
Okay, this isn't something that you can just find using like view properties. This is something you use through the command line that, or well, I mean, what we've been using in Raspberry.
this is something that will have to be created through your scripts. Like you're collecting your data through your sensors.
Yeah.
Now you have to take that data and send it in generally a JSON format.
Okay.
So we'll get into kind of how to create this data a little later, not tonight, after winter break. But this is how your devices are going to communicate. Now last slide for this chapter is your data capture requirements. These are generally picked by your consumer, your customer, so to speak. And the main one is frequency. How often is your data going to be collected? Are you having one device that's collecting data every hour? Or do you need it collected every minute or 2 minutes? However often you need. Sometimes daily is good enough. Sometimes you need hourly. Data staleness is something that goes along with frequency, in that how long is your data allowed to sit there without being refreshed? So let's say you have 2 sensors. Each of these are refreshing at an hour interval, but your data staleness is only allowed to be half an hour or 45 minutes. Now you can set one sensor to read on the top of the hour, like 12 o'clock, and then the next sensor to read at 12:30, and then keep alternating every half an hour. That means your data staleness is at most 30 minutes, assuming both sensors are working properly. So any question on frequency or staleness? All right. Delivery guarantees. There's generally two that the book has, which is at most once or at least once. So your low priority data, like your everyday, you're getting this data every hour, that is going to be sent by your device one time. And that's going to hit your message bus, it's going to be processed, it's going to be great. But now, all of a sudden, your data spikes. Like you're monitoring some high temperature stuff in a steel mill, and all of a sudden a furnace shuts off and your data drops by 2,000 degrees. That's a problem. Now you have an alert that's going out. That's going to fall into your at least once. You may send that alert out 4, 5, 6 times just until it's acknowledged, just to make sure that the person that's supposed to be monitoring it gets that message. So you have your at most once, and then your at least once. And then of course, cost. Cost is the other big data capture requirement. When you have more data to send out, that's going to increase your power usage. That may not matter in something like an industrial setting. You plug it into the wall and the company just pays the electric bill. They probably don't even know how much it costs. It comes out automatically. But if it's in the middle of a field and you have to use solar arrays or something, power is now expensive because you have to pay for the solar panels. If you need to be sending data more often, how big are your battery backups? How much data are you going to store? Because storage is not free. And actually neither is, especially if you're using AWS, your data ingestion and data egress, where you send the data back out, that's not free either. So how much data are you sending and receiving, and how much is that going to cost your customer? Because you're not going to be footing the bill. The customer is going to foot the bill. And if they're expecting their data to cost $200 a month, and you hand them a product and now it's costing them $2,000 a month, they're going to have a problem with that. So now you have to look, well, is my frequency too high? Am I expecting too little time in my data staleness? Or am I setting the messages just too many times? It's something that's supposed to be at most once, set to send multiple times. These are all kind of the data capture requirements that go into designing an IoT device. So, any questions on that? All right, hearing none, I'm gonna kind of change gears. I don't have a live demo tonight, but I do want to discuss the project. The final project, which I am, by the way, you weren't here next week, is winter break. There is no classes. I will not be on Zoom next Tuesday. I'm also hoping to move next week. So feel free to email me, but just know it might be a day or two before I respond. But that being said, I have opened up here's the assignments. Lab 1, no. The IoT project proposal. I'm going to view this as I do. Thank you. I just got the call from the mortgage banker, like right before class started, said I was clear to close on the house. So, project proposal. I am not looking for a ton in this proposal. this will be a Word document or PDF. And it will have 4 sections in it. It will have your problem statement, what you're proposing is the solution, the technical feasibility of it, and your implementation plan. Your problem statement can be anything. I have too many birds in my yard and I want to see how many are standing on a patch at any given time. So I'm
I like it.
gonna make a device that has a pressure sensor to count birds.
Okay.
That kind of combined the problem statement and the solution. Problem statement being I have too many birds, solution being I'm gonna count them with the pressure sensor.
How many
Could you use that as like say how often are the chicken I have chickens. How often are they going into the box to try to lay an egg? Or
Yeah.
when does one go into lay an egg?
Yeah,
Perfect. Thank you. You helped me with my
Um,
assignment.
How would I don't know if this is what you're asking, but are we actually making a full-on sensor for this?
well, that's the other thing. I said you could either do the sensor side or the data acquisition side.
Okay.
So, because IoT has those 2 different aspects where you have your data producers and your data consumers. So as long as you can create something that will take hypothetical data, because I don't expect everybody to go out like, for the chicken, you
I
would
was-
probably use some sort of infrared sensor to check when a beam is broken to count chickens going in and out. I don't expect people to buy that.
I was more curious about how much Linux do we need to know to be able to get that? Because I thought we were going to talk about that.
Yep, and we are.
Okay.
I would not worry about the technical side too much
Okay.
at this point. There is a technical feasibility of this. And really, I'm looking for, this is how my data is going to be sent. This is kind of how it's going to be received. What sensors might I need hypothetically if I don't have those on hand and don't plan on getting them?
So we're talking about a theoretical sense in here. We're not
Yeah, if you're not
talking
actually
physical
building,
part.
if you're not actually building the sensor side, I want the ingestion side to be built. So like, if it can take in hypothetical data,
Mm.
perfect. Because I don't expect everybody to go out and get sensor arrays.
Okay.
If you have a sensor you can use that is analogous to it, that works fine. Like for the chicken project, I don't expect you to get an infrared LED and a receiver to count chickens, but if you have a button that you can simulate a chicken walking through, fantastic. That will work.
Nah, I was thinking probably like either a pressure or a heat sensor, like seeing if it gets to a certain temperature.
Those would work perfectly fine too. If you want to propose multiple different solutions, sometimes a heat sensor might not be sufficient enough because let's say something else gets into the coop. But you
True.
know that a chicken's average weight is between X and Y. So you
Yeah.
can also add a pressure sensor to validate the original data.
And
you know-
I can also weigh all my chickens.
You could do that too.
They would hate me.
Then we have the implementation plan, which is kind of something for yourself to map out between the time that the project actually starts until the end of the semester to kind of give yourself milestones. Like if this week I want this done, next week I want to get this far,
Mhm.
so on and so forth. So I keep bees. It's one of my hobbies. So I needed a way to track the internal and external temperatures of the beehives, especially in winter, because dead hives happen sometimes.
Mhm.
Whether moisture gets in and it molds in the hive, this is a lot of stuff that people don't realize happens, but moisture can kill a hive quicker than the cold. So I created my own IoT device to monitor. Now, this data is very, very old because while the device itself worked, it was not Rottweiler friendly, and he tore through it and ripped it out of the ground. But this monitored all of my temperatures for each hive. I have an internal and an external temperature, and I also used the Raspberry Pi camera to kind of track the comings and goings of bees, which alerted me to a couple different issues that I had at the time. But this was using the Raspberry Pi Zero W. So I just use Wi-Fi as my connectivity. It used 2 temperature sensors, one for internal, one for external. And I had 2 hives that I was monitoring. Now, looking at this data, you can see, oh, well, this dropped right here. Like you have this downward spike in temperature. What happened? I opened the hive. This data can show when something's really wrong. Like if something had broken into a hive, you could see that in the data, and I would have gotten alerts on it. Now, this new stuff, that's kind of just hard-coded. I have a form that I filled out when I was keeping track of that, but it was monitoring my data so that I could just look at my phone and be like, oh, hives are good, go on with my day. And then I had the pictures to go with it. So this was a device that I created last summer. So how did I do it? I used Python, and every now and then I just connected this to a schedule in Linux using cron, which is the internal scheduler. You can do it all the way down to every minute, which I had problems with. Can anyone guess what the problem was when I had it at 1 minute?
Too open. I like.
Those photos, they filled up my databases within a week.
Yeah, that makes
I had 2 gigs of storage on each MySQL database, and those photos taken every single minute of every day filled up my storage.
Why
And
did you want to take that many photos though?
because I was obsessive, I didn't think about it. I didn't calculate, well, these photos are this big and my storage space is 2 gigs. How many photos can I take?
Are you looking for something really specific in each of those minutes though for that? Like I know you said.
That's the thing, I wasn't. I was planning on doing just time-lapse stuff and having fun with it, but it killed my entire system because my web host actually locked my account until I took care of it.
That's-
I couldn't store anything in any of my databases because of these pictures. And I could have done things differently because it still took pictures at night. Like those pictures were just black. What's the point of that? I could have put that on a schedule. I could have added more compression. There's a lot that I could have done differently, but it's something that I didn't think about when I first started. So basically I have this Python script that reads the temperatures. It uploads the data, captures the image. It does a little image cropping because the device wasn't set up that great. So it's a manual cropping. And then I upload the data to my website. And that's how this device worked. It used HTTPS to upload the data to this URL. And using Python, it just uploaded the site for me. And it was relatively easy to maintain, easy to set up, and easy to troubleshoot when there were problems. And this entire Python script, not counting what I commented out, 116 lines to drive this entire site.
Wow.
The site itself took a little more, but the actual data sending, which is as far as I pretty much expect anybody to get. I don't expect you to create an entire website and format it and make it pretty. Although that would be probably a good extra credit opportunity. But but you won't be required to make like a full front end system. So that's a device that I created. I will probably be bringing that in at the next lecture because it did use multiple sensors. It used the Raspberry Pi camera, which most people don't use.
Is there a camera on the Raspberry Pi?
There is,
Yes, there is.
if you look
Okay.
at the headers on the Pi, there's a ribbon cable header that's labeled camera. That goes to a little tiny camera. It costs literally about $10 on Amazon.
Okay. Oh, I thought it was included on it, like that tiny.
No, it's
No.
a separate add-on, but it is relatively inexpensive.
Most of the things like add-ons for the Pi are typically inexpensive.
Okay,
Yeah,
so like,
it's
yeah,
good.
this one,
Oh. Look, there's an Arduino one which could probably work too.
yeah, I believe they are compatible, yeah. Now, the problem with some of these cameras that I noticed, they don't all have autofocus. So some of them have a little lens that you have to manually turn, and I just couldn't deal with that with this Beehive device because I had it so waterproof that it was a pain to get in and out. So I had to find a camera that had autofocus, so that cost me a little extra. But in general, these devices are super inexpensive, and Python can read them directly as long as you have that camera port enabled, because Pis do not have it enabled by default. So that is kind of how I created this entire site. So this camera probably costs $15 to add on to any Pi that I have. And then it just sends the data based on, I can't remember what I ended up, I think I went hourly with the data. But you can see every night where it would dip down in temperature, but the internal temperature was always 10 to 20 degrees warmer than outside, even in the summer, because bees like it about 90 degrees for optimal eggs. So that is kind of the rundown. Any questions on the project proposal requirements? So I have scheduled this to be due in 2 weeks. So think about what you might want to do. If you can come up with a problem statement that makes any sort of sense or makes me laugh, you're probably going to get full credit. This is the
What do you mean, make you?
this is the exact rubric that I will be using. So
Just come up with like.
Now
really
I have a
kind of
question.
yeah,
What if we instead of building like a true website, like what if we make a mock-up website? It's not recording data online actually, but it's like an example of what it would look like.
Have to think about that. I'm still writing the final requirements for
Yeah.
the project. But especially on the data processing side, if that's the side you want to go with, that could definitely work. Definitely be part of that as extra credit. There will also be one more kind of small lab coming up after the break. Based on the feedback that I got from people about Linux, the Raspberry Pi, and some of the challenges with that, I don't expect the second lab to be any more difficult than the first lab. So, question? Oh. So for this one, it's just going to be a PDF or Word document with these 4 sections. So any questions at all on anything that we've discussed tonight? Any questions on anything we've discussed in the class so far? All right. Well, I am not gonna keep anyone any longer than necessary. I'll still be around for probably about half an hour if there's any questions. So feel free. I will also be uploading the slide deck and the recording tonight.
The slides are already up online.
Yep. Yep, they should have launched about an hour ago or 10 minutes ago. I can't remember what time I set them for, but I uploaded those before I left home because I don't carry flash drives with me.
This is making me think of some of the.
So- I look forward to seeing the proposals, and with this one, if you have a section, let's say, like your technical feasibility is just completely off, I will give an opportunity to redo it to bring the grade up. So don't worry too much about that. There might be some back and forth with these proposals.
Wait a second, so for the feasibility though, it has to be, we have to keep this in reality, yes?
Preferably,
Okay.
preferably. So, if you have any questions, feel free to email me. I've had a couple students message me on Discord. I'm in the EMU servers. So have a great night, and I will see everybody after the break.
Okay.
So, Professor, can I ask you a question related to Lab 1?
Sure.